All right, I wanted to make a quick video of the last two problems that I wanted to go through on the homework. I started the 20.84, but I didn't finish it. We ran out of time. So anyway, it was the mass defect for nickel 58 problem. All right, so a mass defect is when you have your nickel 58 that is broken into its individual protons, which is 28. So you get 28 protons. And then your 58 is your mass number minus 28. That's your 30 neutrons. All right. And so we're going to find the change in mass. And so you look up your mass for your nickel. All right. But on the chart, it is the element mass. It is the mass with electrons. And so you have your 57.935348, but you're going to have to subtract the 28 electrons that go with that number. All right, and so you have your 28 protons. You get the mass of a proton right off of your chart. That is the 1.007277. You've got your 30 neutrons. You get that mass right off your chart, 1.008665. Those numbers will be given. Then you have to take your 58.935348 and then subtract your 28 times your mass of your electron. All right. So when you do that, you're going to get your change in mass. And anytime you're doing a mass defect, that is always going to be an endothermic reaction. And so that means that your change in mass is always going to be a positive number. All right, so when you get those numbers, you have for your 28 protons and 30 neutrons, 58.46, 3706. And for your mass of your nickel, minus the 28 electrons, 57.919976. So your products minus reactants gives you a positive delta M of 0.54373 AMU, or I always use grams per mole. I do not use AMU. All right, so when I want to get that into energy, I'm going to use my delta E is equal to delta MC squared. I know I'm going to get joules, so I know I have to have my mass in kilograms, because a joule is a kilogram meter squared per second squared. So I convert my grams per mole into kilograms per mole by dividing by 1,000 grams in 1 kilogram. And so now I have my number in kilograms per mole, and that mass defect is a 5.4373 times 10 to the minus 4 kilograms per mole. And now I multiply that by c squared. C is a constant, will be given 2.998 times 10 to the 8th meters per second squared. And a kilogram meter squared per second squared is a joule. And so you have your first answer, which is going to be calculate your energy in joules per mole. All right, so the question may ask for what is the energy in joules per nuclei. If that is the question, you have joules per mole, and you know that there are Avogadro's number of nuclei, 6.022 times 10 to the 23rd in a mole. So when you divide that by Avogadro's number, you get your energy to be 8.115 times 10 to the minus 11 joules per nuclei. The question could ask, what is the energy in joules per nucleon? Nucleons are the protons and neutrons in the nucleus. So when we're talking about nickel 58, that means there are 58 nucleons, 28 protons, and 30 neutrons. So you have in one nickel 58 nuclei, you have 58 nucleons. So we divide by 58, and we get our delta E is 1.399 times 10 to the minus 12 joules per nucleon. All right, but the usual units for energy in these problems are MeV, mega electron volts. And so this conversion will be given. There is 1.602 times 10 to the minus 13 joules per mega electron volt. All right, and so when you get your joules to cancel your joules, you get MeV per nucleon. And that is the usual answer when you get a binding energy problem. All right, and that for this answer is your 8.734 mega electron volts per nucleon. Again, that's the usual answer, the units that they want when you're doing a binding energy. All right, but it could be MeV per nuclei. So once we have nucleons, now we're just going to do this in reverse. Okay, so there's 58 nucleons in one nickel 58 nuclei. And so when we multiply it by 58, we would get 506.6 MeVs per nickel 58 nuclei. All right, but what if we wanted it in MeV per mole? Okay, again, the most common answer and the answer that you're normally going to get is the MeV per nucleon. But if you want MeV per mole, now you have to multiply by Avogadro's number so that your nuclei cancel your nuclei, and now you have MeV per mole, and that is 3.051 times 10 to the 26 MeV per mole. And then, just for the heck of it, we can go back and change it to joules per mole by doing the conversion factor 1.602 times 10 to the minus 13 joules per MeV. So the MeVs cancel. And we're back to our first answer, which was 4.887 times 10 to the 13 joules per mole. All right, so that's just changing units. So you have to give the units that are asked for. All right, the last question that we did not go through, and it's kind of a hard question, so I'm going to go through it. It is 1942 Part E. It's an oxidation reduction. So you have your CuS, NO3 minus, goes to Cu plus 2, NO, S8, and it's in acid. So again, the first thing you got to do is find your oxidation numbers, Cu and S and N and O and Cu and N and O and S. All right, so in a binary compound, your S is always minus 2, and that makes your copper plus 2 because the overall is neutral. All right, oxygen in compounds is minus 2, 3 of them is minus 6. Your N has to be plus 5 to give an overall of minus 1. Copper plus 2, it is a monatomic ion, so it is the oxidation is the same as the charge, plus 2. NO, oxygen's minus 2, so nitrogen is plus 2 because the overall here is no charge. And S8 is sulfur in its natural state, and so that is an oxidation number of 0. So with the sulfur is going from a minus 2 to a 0, so that is an oxidation. We're going to lose 2 electrons per sulfur. And when you have your S8 here, that means we're going to have 8 sulfurs. And so we will put a coefficient of 8 in front of our copper sulfide. All right. So, well, once we do that, then we have to put an 8 in front of our copper plus 2 to balance that as well. All right. And so we have minus losing 16 electrons. For your nitrogen, it's going from a plus 5 down to a plus 2. It is a reduction. All right, so we're going to gain 3 electrons per nitrogen, but there's one nitrogen, and so we're gaining a total of 3 electrons. All right, the copper plus 2 is not changing oxidation. It's copper plus 2 on both sides of your reaction. All right, so we bring down our 8 CuS, we have our 8 Cu plus 2s, and we have our S8. And again, that is going to lose 16 electrons, so we put 16 electrons being released, product side. All right, our NO3 minus going to NO, that again is going to gain 3 electrons, so we gain 3 electrons plus 3 electrons, so on the left side. All right, so now that we have it broken into our oxidation half reaction and our reduction half reaction, we now know that the CuS is our reducing agent. It is the reactant of your oxidation half reaction. And the NO3 minus is your oxidizing agent. It is the product of your reduction half reaction. All right, so now we're going to balance the charge using H plus because it says here that we are in acid. All right, and so when you look at your oxidation half reaction, 8 CuS, they're neutral, no charge. You got 8 Cu plus 2s, that's plus 16. You got S8, that's neutral. And you have 16 electrons. So you have plus 16, minus 16. So you have 0 on both sides. There's no H pluses required for your oxidation half reaction. For your reduction half reaction, you have 1 minus with your NO3 minus, and you have 3 electrons, so 3 more minuses. You have a minus 4. On this side, you have NO, no charge. So you add 4 H pluses so that you have a 0 charge on the left and a 0 charge on the right. Then we balance our hydrogens and oxygens with water. So you have 4 H pluses, you need 2 H2Os. You check your oxygens, you got 3 on this side, you've got 1 plus 2, 3 on that side. So you have your balanced reduction half reaction. Now, before we can add them up, we have to have the electrons lost equal the electrons gained. So we have to multiply our oxidation half reaction by 3 to get 48 electrons lost. And we have to multiply our reduction half reaction by 16 to get 48 electrons gained. All right, so when we do that and we bring down our products, our reactants and our products, all right, so we have our 3 times 8, 24 CuS, 16 times 4 H pluses, that is 64 H pluses, 16 NO3 minuses, 16 NO3 minuses. Our 48 electrons gained is going to cancel our 48 electrons lost, so that is gone. We have our 3 times 8, 24 Cu plus 2s. We have our 3 times S8, so 3 S8s. Again, our electrons are gone. We have our 16 NOs, and our 16 times 2, 32 H2Os. So that is our overall reaction. We can check the charge. All right, so you have 24 CuS's are neutral, 64 H pluses, that is plus 64. 16 NO3 minuses, that's minus 16. So your total on the left is a plus 48. 16 NO neutrals is 0. 24 Cu plus 2s is plus 48. 3 S8 neutrals is 0. 32 H2O neutrals, 0. Again, you have your 48 on the left and your 48 on the right. And so that is how you balance that last oxidation reduction reaction. And so that is the end of the homework for exam 4.